Welcome to subnetting. So what is subnetting? Subnetting is the process of creating IP network ranges or child subnetworks from a given parent IP network range by using classless addressing to change the subnet mask notation, also known as the CIDR notation. CIDR means classless inter-domain routing. So subnetting is the process of creating children subnetworks from a parent network. To understand subnetting, we need to see the effect of changing the classless inter-domain routing notation of the parent network on the number of available subnetworks and hosts. So that's what we're going to do next. So I was able to set up a network, and here we have with headquarters in London. Then we also have branches in Toronto, New York, Paris, and Abuja. So here we have different parent networks issued to the different networks that connect to the headquarters. For example, here we have 42.10.10.0. Here we have 12.12.30.0. Here we have 34.5.5.0. And over here we have 20.5.5.0. And now we have to issue IPs to devices that are connected or located within that branch. And if you look down below, we have .10, .20, .30, 40, 50, 60, 70, and 80 that has been given to the host IP addresses. If you look down here, you'll see that the network range of this IP address that has been given is 20.5.5.1 to 20.5.5.254. So it means that we can get about 254 host IP addresses that we can issue to network devices in this branch. But right now, this branch has several departments. For example, you can see that we have admin, we have the accounting unit, we have the IT, and we have the HR. And apparently, all the devices are within the same network. So let's take a look at the lab and see how these devices are connected. So over here is my packet tracer, and as we can see over here, we can see that, we can see that we have the headquarters and the branches, and in Abuja we have all the departments. So don't worry about how I was able to set up this lab, because in subsequent videos I'm going to teach you how to set up these labs with packet tracer when we go into routing and switching. But for now, what I want us to understand is that these devices, host devices, are connected to this network that has been given, 20.5.5.0, which has a CIDR notation of 24. That means the first 3 octets are the network portion, and the last octet is the host portion. And that's why it's been split to all these devices. So all these devices fall within the network that has been given. So if I want to test that there is connectivity, that means because all these devices are on the same network, they should be able to connect together. I would want to issue these IP addresses to these devices and make sure that they can ping each other. So let me start with this one. This one is .10. So I'll simply go to config and I'll go to the fast Ethernet 0, which is what is connected to the switch. And I want to make sure that the static is giving the IP address as .10, and also we have the subnet mask, which is /24, which correlates with that. That's the first 3 octets is the network and the last one is the host. So this is fine. So I'm going to ping from this device to another device over here. So maybe we'll call that PC7, and PC7 should have an IP address that also falls within this network. So let me open that. Now go to config and go to interface and fast Ethernet 0, and now nothing has been issued, so I'm going to type that in 20.5.5.80, and the subnet mask would be 255.255.255.0, which shows that it is /24. So I'm going to close this, and now if I ping this, I should be able to, if I ping PC7 from PC0, I should be able to get a successful transfer of the ping packet. So let me try that. So I'm going to open that, and I'll go to desktop, and I'll go to command prompt here, over here. And what I'm going to do, I'm just going to say ping, and I'm going to ping PC7. So I'll say 20.5.5.80, and I'll ping that, and I should get a successful reply. It sent 4 packets and received back 4 packets, which means it was successful. So let me try and ping another IP address that is not currently issued out. So let me just try and ping 20.5. Maybe I'll say 15, which has not been issued out, and I should get a failure of the ping, and as you can see, it will give me request time out. So I've received request timed out, which means that it wasn't successful. So if I also try to ping an IP address in another network, maybe in New York, and I'm going to take 12.12.30, and I'll take .1, or let me just say .2, and I'll ping that. I should also get a request timed out because it's in a totally different network. So the first one failed because it's not been issued to any network device within the network, and the second one has failed because it's not found within the network that it belongs to. So let's go back and see how we can continue to analyze the network. So we're back here, and this is the network we just came from, and we successfully pinged from PC0 to PC7. So we can see here that this is the IP address that was given, 20.5.5.0. It shows us here the network range, which is 0 to 255. Because the first 3 octets is network portion, so only the host portions will be changed. So we have the first IP address, which is the network address, which is .0, the second IP address, which is .1, which is the first available host address to be issued out. Then we have the second last IP address, which is .254. That means the second to the last, as the last available host address. And we have the last IP address, which is 255, which is .255, which is the broadcast address. So we can see now that this is all in one network, and all devices should be able to communicate with each other. And we can also see here the formula for finding out how many networks and hosts we have available. So we have the number of available subnetworks is 2 to the power of n, where n is the number of new network bits. So in this case over here, this is the last octet of the subnet mask, and we can see that all these were the host portions. So there was nothing that was borrowed to make a new network bit. So all these bits are the host bits, so nothing was taken. And that's why we have 2n, which is equals to 2 raised to power 0, 0 meaning we didn't take or use any bits as the extra network bit, and that 2 raised to power 0 gave us 1. So we have one available network or subnetwork. So the number of available hosts we have within that network or subnetwork is 2 raised to power h minus 2, where h is the number of available host bits. So over here, the available host bits we have is 8, because remember this is the last octet. The first 3 octets have all ones. That's why it's 255.255.255. Then the last one, which is 0, has all zeros. So all parts here are all host bits. And that's why we have, if you count them, they are 8 in number. That makes up the 4th octet. So you take it here and say 2 raised to the power of 8 minus 2, that is 256 minus 2. So we have 254 available hosts, which is true, which is what we have here, from 20.5.5.10.1 to 20.5.5.254. That is with the exception of the network bit, the network IP and the broadcast IP. That's why we have -2. So we only have one subnetwork available, or one network, which is the parent network. So let's assume that we need to separate the HR department from every other department. And what that means is that we can't have one single network only again. We need to have more than one network or subnetwork within the main parent network. So in this case, we have the parent network, which is 20.5.5.1 to 254. And now we've decided to split it into 2 subnets. The first subnet has 20.5.5.1 to 20.5.5.126. And let us take note of the CIDR notation, which it shows /25. So what that means is that we have taken one bit, or borrowed one bit, from the host portion, and we've now made it /25. So this is classless addressing. And we also came here and did the same thing, 20.5.5.129 to 20.5.5.254. And it's the same thing /25 notation. So you can see how the two subnetworks are separated logically by their IP addresses. So let's see how that was done. So this is still the last octet of subnet mask, and we can see where we borrowed the 1 bit, which is the first bit, and we made it to be 1. So that made it to have 128 as the subnet mask, which is what we have here. So 255.255.255.128. And you can see that we have 2 subnets that was created from this network. So let's see how we did that. So using the formula, we said number of available networks, which is 2 raised to the power n. So we said 2 raised to the power of n, which is 2 raised to the power of 1. So we have 1 network bit that was borrowed, and if you come here, you can see the 1 here. So that made it 2 available subnetworks, and that is what we have here. So how do we know the hosts that are available for each of the networks? So we say number of available hosts is 2 raised to power h minus 2, and h in this case is the remaining hosts, available host bits. So if we come back, since we borrowed 1 from the network, it means that we are left with 1, 2, 3, 4, 5, 6, 7 host bits that were not touched. So it means that we have 7 available host bits. So 2 raised to power 7 is 128 minus 2 is 126 available hosts. So it means that we have, for each subnet, we have 128 hosts, of which 126 are available to be issued to devices. That means 20.5.5.0 is the network, and 20.5.5.127 is the broadcast address. So what we have in between is what we saw in the chart here, which is 20.5.5.1 to 20.5.5.126, which are available to be issued out. So how do we now know exactly how to specify where the network starts and where the network ends. So an easy way to do that is to look at the subnet mask, and you can see that the last octet ends with 128. So what we do is would use the limit, which is 256, to subtract it from the limit, and what you will get at the end is 256 minus 128 is 128. So with that idea, you know that each network has a step of 128. That means we should have from 0 to just before the next network, which is 128. So 0 to 127 and 128 to 255, just before 256. And that's what we have here. So that's the easiest way to be able to predict how the networks would start and where they will end for each of the sub networks that will be created. So let's take a look at another one. So now, assuming we also need to separate the IT department from every other department along with the HR, it means that we should have at least 3 subnetworks. So in this case, we were able to get 3 subnetworks, as you can see here. Network 1, subnetwork 2, and subnetwork 3. So in that case, what we did was we had to borrow 2 extra bits from the given parent IP address. And that's why we have 192 here. So we borrowed the 2 extra bits, and we also have 192 as the within the subnet mask. And that was able to give us /26 CIDR notation. So we have 4 subnets that were created from that. And how did we get that? Using our formula, we found out that number of available subnetworks will be 2 raised to the power of n. So n is the number of borrowed bits, and in this case we borrowed 2. So that will be 2 raised to the power of 2, which will be 4 available subnets. And that's how we have these 4 available subnets. So what about the number of available hosts? We use the same formula, 2 raised to the power of h. So since we borrowed 2, it means that we have 6 bits that are remaining from the 4th octet as the host portion. So we'll use that 2 raised to the power of 6 minus 2, that is 64 minus 2, which gives us 62 available hosts. So this means that for each subnet, there are 64 IP addresses, of which 62 is available to be issued to devices. So in the same way, how do we know the start and end of each of the subnets? So we are given that the subnet mask ends with 192. So we'll take the limit again. So 256 minus 192 will give us 64. So it means that it has a step of 64. So we'll start from 0 to 63, just before 64. Then we'll have 64 to 127, just before 128, because this is an increment of 64. So 128 to 191, just before 192, because 128 plus 64 will give us 192, and 192 to 255, just before 256, because 192 plus 64 will give us 256. So that it makes 4 subnetworks. So that's the easiest way to be able to create your subnetworks. And that's why when we go back to the chart, we can see that this first one was from .1 to .62, which we have here as, because the .0 is the network portion. So .1 will be the first available host portion, and 60.63 is the broadcast address. So .62 should be the last available host portion, and that is why what we have here. And in the same way, we have 20.5.5.1292.190. And if you bring it down here, we can see that that's the third subnet. So this second subnet was left out. Only subnet 1, 3, and 4 were used. So that's why we have .128, which is 129 is the first available host address, because 128 is the network address. Then over here we have the broadcast address as 191. So the last available host address will be 190, which is what we have here. And over here, which is third subnet, you can see that it starts with .193 and ends with .254. And you can see that .192 is the subnet address, 193 is the first available host address, and 254 is the last available host address, because 255 is the broadcast address. So what if we have more departments and we need to create more networks from the parent IP address? So what do? It means that we need to consider the number of subnets we should have. So having 4 more departments plus the 3 departments we already have would make it 7 departments. So it means that we need to have at least 7 departments or subnetworks that are available for the departments. So we can see that in this case we had to borrow 3 extra bits, and that's why we have 224, which is over here as .224, because we borrowed these 3 host bits. So we can see we use the same formula, that's 2 raised to the power of n with 2 raised to the power of 3, which gave us 8. Why 3? Because we borrowed 3 bits, and that is the 8 available subnetworks. And the number of hosts we'll have is 2 raised to the power of 5. Why? Because if we borrow 3, we are left with 5 host bits. So 2 raised to the power of 5 minus 2, that's 32, minus 2, which gave us 30 available hosts. So how do we get the 8 available subnetworks? Remember the same thing, 256 minus 224, which gives us 32. So it means that we'll have 32 steps. So what it means is that we'll have from 0 to 31, 32 to 63, 64 to 95, 96 to 127, 128 to 159, 160 to 191, 192 to 223, 224 to 255. So those are the 8 subnets we have. So if you look at this, it means we have the first subnet, which is from .1 to .30. Remember, the .31 is the broadcast address and .0 is the network address. And the second one we have is .33 to .62, because .32 is the network address and .63 is the broadcast address. And next we have .65 to .94, because .64 is the network and .95 is the broadcast. And then we have the other 8 subnets, which is .97 to .126, because .96 is the network and .127 is the broadcast, and it's the same with the other 4 subnetworks. So let's try our hands on 2 more. So what if you need to have a total of 15 subnetworks from the given parent network? Maybe you have 15 departments and you need at least 15 subnetworks. So what would you do to subnet to create 15 subnetworks? If we borrow 1 bit, remember our formula is 2 raised to the power n. So 2 raised to the power 1 will be 2. So that will be 2 networks, which is less than 15. So if we borrow 2 bits, that will be 2 raised to the power 2, which will be 4, which is still less than 15, so that won't work. If we borrow 3 bits, that will be 2 raised to the power 3, which is 8, which is still less than 15, that won't work. If we borrow 4 bits, that will be 2 raised to the power 4, which is 16, which is just above 15. So that means we would need to borrow 4 bits. So 4 bits from the host portion will be made the network bits. And that's why we have 240. So the subnet mask will be .240. So it means we'll have 2 raised to the power 4, which will be 16 available subnetworks. And the number of hosts we'll have is 2 raised to the power 4. Why? Because we have 4 bits that have been untouched as the host bits. So that will be 16 minus 2. So we'll have 14 available hosts. So what that means is that we will have 16 subnetworks with each having available host IP addresses for network devices. So let's try one more. So what if you want each of the subnets to have at least 5 available host addresses in each of them from the given parent network? So what that means is that each of the subnets should have at least 5 available host addresses to issue out. So let's try and see if we are left with just one bit for the host portion. So using that formula, that will be 2 raised to power 1 minus 2. So 2 raised to power 1 is 2, 2 minus 2 is 0. So it means that we won't even have any IP address to give out to any device. So what about if there were 2 available host bits from the fourth octet? So it means that that will give us 2 raised to power 2 minus 2, which will give us 4 minus 2, and that will leave us with 2 available IP addresses to be given out, and what we require is 5. So that will not be suitable for as a solution for the problem we have. Let's try and see what will happen if we have 3 available host bits. So using the formula, it will be 2 raised to the power of 3 minus 2, and that will give us 2 raised to the power 3, which is 8, minus 2 will give us 6 available IP addresses, and that is just above the 5 we require. So what it means here is that we would have the network portion will be 5 borrowed bits, and the 3 which will be untouched is what will make up the 6 available host addresses. So if we use in the formula, we say 2 raised to the power of n, which is 2 raised to the power of 5, to give us 32 available subnetworks, and the number of host bits we'll have will be 2 raised to the power of 3 minus 2, that was 8 minus 2, that was 6 available hosts. So it means we would have 32 subnetworks with each having 6 available host IP addresses for network devices. So this is the summary of what subnetting entails.